Hello, everyone. Thank you for coming today. Today, I will introduce the LCDC demo application. Today's introduction mainly includes the following topics. First, the software and hardware environment will be introduced. Then, the software compilation and download and experimental verification will be introduced. Finally, the important codes will be briefly introduced. This report is mainly introductory content. For the technical details, you can learn more about them through the SDK online documentation. The LCDC demo application provides a simple example of how to use QSPI interface, I8080 interface, or SPI interface to communicate with a liquid crystal display controller. The LCDC demo supports the RTL87X3E, RTL87X3D, and RTL87X3EP development kits. To quickly build a development environment, please refer to the SDK online documentation. The default supported display driver IC model for LCDC demo is SH8601Z. For convenience in testing the LCD, we have developed an adapter board. Simply plug the adapter board into the card slot of the EVB, and it is possible to test and use the LCD. Here we show the EVB and screen adapter board of RTL87X3E and RTL87X3EP. Please refer to the SDK online documentation for the mapping relationship between the LCD and the EVB pins. Here we show the EVB and screen adapter board of RTL87X3D. Please refer to the SDK online documentation for the mapping relationship between the LCD and the EVB pins. You can configure the LCD device used by the LCDC demo application by modifying the macros target LCD device. The supported LCD devices for the LCDC demo are shown in the table. The following is an introduction to the compilation and download methods of LCDC demo. Taking the LCDC demo of RTL87X3E as an example. First, open the LCDC demo project file of RTL87X3E, then select and compile the corresponding target. When the compilation is successful, the app bin file will be generated. Download the app bin and resource bin to the EVB board, and finally press the reset button, and the LCDC demo application will start running. For detailed steps, please refer to the SDK online documentation. Next, we will introduce the experimental verification of the LCDC demo application. Press the reset button on the EVB board and the LCD will be filled with blue. The LCDC demo project is located in the board EVB LCDC demo directory. The application source code is located in the SRC sample LCDC demo directory. The structure of the LCDC demo project is shown in the figure. This section will introduce some of the source code used in the application of this project. When the application is powered on or the chip is reset, the main function will be called. In the main function, the function app.io resource request init is first called to request the DMA channel used for LCD screen refreshing. Then, the pins used by the LCD are configured. Next, the function RTK LCD HAL init is called to initialize the LCD. Finally, the function RTK LCD HAL RECT fill is called to refresh the screen to a blue color. Below, we will take the screen with QSPI interface as an example to introduce how to adapt your own screen to the LCDC demo project. Firstly, it is necessary to implement the screen initialization function and add it to the function RTK LCD HAL init. The specific content of the initialization function is to send the screen initialization instruction to the screen through the QSPI interface. The screen initialization instruction is provided by the screen manufacturer. The implementation of this function can refer to the function sh8601a init of sh8601z. Next, it is necessary to implement the function for setting the screen column address and row address, and add this function to the function RTK LCD HAL set window. The implementation of this function can refer to the function LCD sh8601a xpy 454 set window in sh8601z. If there are backlight control or other control pins on the screen, the initialization part of these pins needs to be added to the function LCD pad init, and the initial state of these pins needs to be set in the function LCD driver init. If these pins need to be set when the screen is turned off, the control of these pins needs to be added to the function RTK LCD HAL set reset. There is control logic for the screen reset pin in the function LCD driver init, and you can modify the timing of the reset pin according to the requirements of the screen used. The SPIC API is defined in FMCAPIEXT header file. The initialization process of SPIC is shown in the figure. The first step is to set pinmux and pad, the second step is to initialize SPIC, the third step is to set the clock of SPIC, and the fourth step is to set the baud of SPIC. Intel i8080 interface for LCD controller. Support 8 bits. Max speed 20 MHz, pixel output counter, width 32 bits. VSync auto trigger i8080 output. The size of TX FIFO is 32 bits multiplied by 16. The size of RX FIFO is 8 bits multiplied by 16. The 8080 API is defined in RTL876X if 8080 header file. The initialization process of 8080 is shown in the figure. The first step is to set pad and pinmux, the second step is to enable the clock signal of 8080, the third step is to set the parameters of 8080, the fourth step is to initialize 8080 according to the set parameters. SPI supports master and slave modes. Support 4 transfer modes: full duplex, TX only, RX only, EEPROM. Support 4-bit to 32-bit data size in master mode. Support 4-bit to 16-bit data size in slave mode. Support up to 3 slave devices in master mode. Support GDMA. The SPI API is defined in RTL876X SPI header file. The initialization process of SPI is shown in the figure. The first step is to set pinmux and pad. The second step is to enable the clock signal of SPI. The third step is to set the transmission mode of SPI. The fourth step is to set the working mode of SPI to master mode or slave mode. The fifth step is to set the data frame format of SPI. The sixth step is to set the clock polarity of SPI. The seventh step is to set the clock phase of SPI. Next, if SPI is set to master mode, set the speed of SPI. Then, select which serial protocol to use to transmit data. Then, initialize SPI according to the set parameters. Finally, enable SPI. The display controller supports internal GDMA. Supports RGB pixel converter. Supports tier trigger, tier input signal directly from display module. Supports DBIB interface. Supports SDI interface. Supports DPI interface. The display controller API is located in the SDKs RCMCU display driver LCDC directory. The initialization process of the display controller is shown in the figure. The first step is to set pad and pinmux, the second step is to enable the clock signal of the display controller, the third step is to set the parameters of the display controller, and the fourth step is to initialize the display controller according to the set parameters.